The generative AI boom is driving the global semiconductor industry toward a massive milestone, $1 trillion in sales this year alone. To process all that data, you need hardware that is exceptionally fast and produced at a scale that was once unthinkable. But looking at that booming global market, Australia's footprint is almost invisible. Despite a strong foundation in university research, the country currently produces 0 microchips in any significant volume, capturing less than 1% of global revenue. The standard for modern computing is the traditional silicon microchip, often referred to as CMOS. Manufacturing one of these chips involves stacking 100 or more microscopic layers, a process requiring over 1,000 distinct chemical and mechanical steps. This extreme specialization has created a hyper-globalized industry. A single semiconductor device might cross as many as 70 international borders, traveling between specialized facilities for fabrication, packaging, and testing before it finally reaches a consumer. This chart compares a standard local manufacturing budget against the cost of a modern mega-fabrication plant. Building a facility capable of churning out traditional silicon chips at high volumes costs tens of billions of dollars. For a nation without an established mass production ecosystem, that capital barrier is virtually insurmountable. Competing directly in traditional silicon mass production is a permanently lost cause for Australia. Survival in the semiconductor era requires a shift in focus toward technologies where specialized knowledge outweighs raw manufacturing volume. The path forward moves the focus away from massive automated factories and toward the advanced R&D laboratories where Australian engineering already has an established foothold. The core of this strategy is a pivot to compound semiconductors. These materials combine 2 or more elements to achieve performance levels silicon can't match. They are extremely difficult to engineer, but they allow for highly specialized, high-margin production at much lower volumes. Take BluGlass, a company based in Sydney. They produce visible wavelength lasers using a compound semiconductor called gallium nitride. Growing this material requires extreme precision, assembling the crystalline structure atom by atom. Because commercial manufacturing of gallium nitride is in its early stages, outsourcing final processing often yields poor results. To maintain quality, BluGlass vertically integrated, keeping everything from material growth to final packaging within their own controlled system. By mastering an exceptionally difficult material in-house, a tiny core workforce of experts captures the full commercial value of a finished, customized device. This technical precision creates a sustainable niche that avoids the price wars of the mass market supply chain. A similar opportunity is emerging in the hardware of quantum computing. Currently, the sheer physical footprint of the equipment required to run these systems is a primary barrier to their widespread adoption. It is a challenge known as the quantum wiring problem. Each qubit requires multiple channels of different colored light to function. But trying to focus all that light into the tiny 3D space surrounding a single qubit creates a physical bottleneck that prevents scaling up. Lumina Corp, a US-Australian startup, is addressing this by using thin-film lithium tantalate. This material allows bulky, 3-dimensional light channels to be compressed down into sleek, 2-dimensional pathways routed across the surface of a flat chip. While the science is proven, scaling the technology exposes a structural gap in the Australian economy known as the missing middle. This is the void between early-stage university innovation and the infrastructure needed for industrial-scale production. Without local capital and mid-scale foundries to bridge this gap, breakthrough intellectual property and startups are eventually forced to move their operations overseas to find the facilities they need to grow. Closing the missing middle requires a specific type of infrastructure, flexible, short-run fabrication plants, or foundries, built on Australian soil. These specialized cleanrooms are designed for agility. They optimize for prototyping, for secure manufacturing, and for pilot runs, allowing companies to refine their designs locally before attempting global distribution. Establishing these sites for defense and critical infrastructure requires deep collaboration and co-funding between government, universities, and private industry. These sectors must act as partners to anchor this technology in Australia. Strategic success involves positioning Australia as an irreplaceable, trusted node in a few specific frontier technologies. The goal is to provide a specialized capability that the rest of the global network relies upon. The window to act is narrow. Experts in photonics warn that the global supply chain is currently in a formative period, similar to the early days of the silicon boom. They estimate Australia has roughly 5 years to jump on this train before the market consolidates around other global hubs. If the country fails to build this mid-scale infrastructure now, it risks a repeat of the silicon era, where the lack of local facilities eventually forced the industry to move elsewhere, permanently shifting the center of innovation to other shores.
And that wraps up today's explainer. Seriously, what a fantastic deep dive into those mind-blowing engineering concepts. I just want to say a massive thank you for sticking around and completing this journey with me. So let's get into it. Did you find these complex engineering concepts as utterly fascinating as I did? To get more amazing construction content, just follow this blueprint. Thumbs up, share, subscribe, and hit that bell. Trust me, that notification bell is the absolute foundation to ensure you never miss our next upload. Which leaves one final question. What incredible structures are we going to build in our very next adventure?